So before starting the new topic, I would like to provide here an overview, the topics we have covered and what we are doing right now. So if you remember that we have been solving previously for our fluid dynamics part of this course, and we have learned the Navier-Stokes equation, and we have solved integral form of the equation, as well as we also have learned the differential form of this equation. Now make sure that in this part we have been solving for the viscous fluid, that is when the viscosity is not negligible. So in this we have been solving for the velocity, the forces, pressure, and etc. for our typical flow field. Now the next part, in parallel we have another theory, which is potential flow theory. This is another methodology of solving fluid dynamics problem, but a simplified approach it is, because in this we ignore or neglect the viscous effects. So this inviscid means non-viscous. And in this regard, we have previously learned stream function and potential function and their conditions for their existence we have learned. Now we will study further details of this potential flow theory and how we utilize it to solve a typical fluid flow problem for our various applications. Now I would like to provide some summary and details the topic that we have been covering, which is potential flow theory. So previously, if you remember that we have derived these two equations for stream and potential functions. These are the Laplace equations and exist for irrotational and incompressible flow field. Now to solve these equations for a typical fluid dynamic problem, there exist proper boundary conditions. So once we go and apply those boundary conditions and solve them, their solution will be obtained. So the solutions are usually in the form of a sum of elementary solutions. Remember that these equations are second order linear partial differential equation, so the solution can be added together. So as I mentioned that the solution will be in the form of sum of elementary solutions that we will be discussed in the next. Now once we have those solution, they will provide some function of psi, and similarly this phi or phi. So once I have that, my next step will be to go and obtain the velocity. So I will obtain my velocity field by taking the derivative of this potential function or this psi function accordingly. All we have learned these. Now once we have the velocity, the pressure can easily be obtained by utilizing the Bernoulli's equation, which is this equation. I can write down this equation for 2 points. So this is the strategy that we follow for solving a typical fluid dynamic problem. So next I will go and introduce some elementary solutions for these equations. Now first of a series of elementary flow that I would like to talk here is the uniform flow, and we will derive the stream and potential function for this flow. So consider a uniform flow with a velocity v infinity along the positive x direction. So this is my positive x direction, and in the vector form the velocity can be represented here in this. From here the u component will be v infinity, so my v component is 0 because there is no normal velocity. So once I go and take this relation for my potential function, then I can easily equate this with v infinity and subsequently obtain this relation for my potential function. Similarly, by following the stream function equation for velocity u, this stream function can be obtained for the uniform flow. So in this way we have obtained the potential and the stream function for our uniform flow, which is first of elementary flow. Now here, second type of elementary flow known as source flow. It is a two-dimensional flow. So a source flow is a 2D flow for which fluid emanates in equal amounts along radial path. So for example, if I have some hole in a wall and connected a pipe through which fluid is coming out of this wall, so this will represent my source. Make sure that the amount should be equal in all direction, and the main velocity here will be my radial velocity, which will be inversely proportional to the distance from the point, that is the radius. Now next is my source strength. The source strength is the volumetric flow rate per unit depth coming out of the source, indicated by this m dot. So I can easily write an expression for my m dot following the mass flow rate relation. Subsequently, I can also write down the velocity, the v for my source, in terms of vector form. So I have introduced a constant of proportionality, this c, and my radial vector. So that is my velocity. Next, I will go and substitute the value of v in this relation and will perform the integration to obtain the source strength relation with the velocity. So subsequently I have substituted the values of v and n cap, which is normal vector in the radial direction. Here is my n and v. So substituting these values here, performing the dot product, and also I will substitute the value of dA. For dA I will consider this small element. For example, if that is a circle surrounding my source, I will substitute the value of dA also. In addition to substituting the value of dA, I have also applied here the limits on theta, which is 0 to 2 pi. And now I will go and perform the integration, find the value of c, and will substitute this value of c to find a relation between source strength and velocity. Now after performing that integration, I have obtained the value of c constant and substituted that value here in this equation, and subsequently I have obtained this equation for the velocity vector for my source. Now and make sure that this component is my VR. For source only VR will exist, however v theta is 0. Now remember the relationship we have earlier for velocity and stream and potential function in the Cartesian coordinate. So I am here providing those relations again, but for the polar coordinates. So make sure that these relations are exist for polar coordinates and make a nice note of these. Now if I know my VR, I can easily utilize one of these relations to determine my stream and potential function, which I will show you next. Now subsequently I will utilize the radial velocity for my source flow to determine the stream function. I will use this relation for VR and have equated this with my radial velocity. So after performing some simplification and integration, I will obtain my stream function. So here you have seen that I have determined the value or the equation for my stream function for my source flow. Similarly, I can obtain the equation for potential function utilizing the respective relationship. So this is my relationship for my potential function is given, equating this with my VR for my source flow. I will go and perform the integration and will obtain my potential function equal to this, and this is my again a constant of integration. So here is the relation for my potential function for a source flow. So next I would like to define my sink flow. So sink flow is nothing but a negative source. So it means that for the sink flow, the fluid will go inside that source instead of coming out, and make sure that equal amount in all the direction. So this is my sink flow. Instead of fluid coming out, it is going inside for the sink flow, and my stream function will be exactly as that of the source but with a negative sign. So for my sink, it is minus sign is there, and exactly same thing as that of my source. So here an important note to mention that this phi function should satisfy this condition that we have obtained for an irrotational flow. So you can substituting the value of phi here and check that. And this del square phi has a definition in the cylindrical or polar coordinate, this definition. So you can easily check that.